Okay, for the next topic, we'll be talking about data engineering with none other than Fein, who will probably give introduction to his talk and his workshop that we'll be mentioning throughout the days by himself. So welcome to the stage, Pete.
Thank you for having me. Let me get my slides going here.
Okay, yeah. So while I'm sharing your slides, so just gonna say that Pete Fein is a consultant at Snakedev, and his topic is called Data Engineering for Data Scientists. Okay.
Great. All right. Thank you, Nick, and everybody at Geekle for inviting me. As Nick mentioned, I'm a consultant. And so today's talk is a very high-level overview of Introduction to Data Engineering for Data Science. And as Nick mentioned, I'll be doing a 3 or 4 hour workshop with Geekle next week on December 1st. We'll talk a little bit more at the end. And just think of this as sort of a teaser to what is a very large topic. I'm actually writing a, 300 or 400 page book about all this. And so we're going to cover a lot. We're going to go real fast. This is really just all slides. There's no demo. And don't worry if your head's going to explode. Like this, we'll have like just to give you just a sense of the tools and things you might do out there. And so what we're going to cover a little bit is some principles of data science and engineering, a little bit about orchestration, sort of how you actually glue a whole kind of data platform together. I'll talk about data quality and also tools that you can use for writing reusable SQL, which is really exciting. Ways of running Jupyter notebooks in production, and then things about operations and development, and then kind of wrapping up. A little about me. I'm an independent trainer and consultant. I've been doing this for the past 12 years and been working in Python and data for almost 20. And sort of beyond just the depth of experience, I also have a lot of breadth. And so in a typical year, I will work with as maybe 10 to 12 clients. So it's about as many as your average engineer will work with in the course of their entire career. And so just it gives me an opportunity to see sort of the insides of what a lot of people are doing, a lot of different companies are doing, and get a sense of what works and what doesn't. As I mentioned, I'm writing a book called The Data Engineering Toolkit for Pearson, which will hopefully be out next year. Books are slow. I was the CTO of a search engine startup in the early 2000s, which is where I learned how to do all this stuff. Search engines are weird. You have like a website and a crawler, but also a data ingest pipeline. We did a little early machine learning, and I've sort of been repeating the lessons I learned, at whole and in part, at kind of increasingly larger scales for the last 20 years. All of which is to say that I'm old. I'm a lot older than I look, and I don't know that I'm any better at this or any smarter than anybody else. But I've just been doing it a long time, and this is really the only thing I know how to do. And so I'm grateful for the opportunity to share some of that experience with you today. And so my background is a software engineer, and my approach to data engineering is to bring software engineering best practices to the data space. And that's kind of both a sort of a challenge and opportunity. Is that we're still sort of figuring out, like, how do we do data software? How do we do it at scale, both in terms of larger data sets in our machines, but also in terms of number of developers. And so it's easy to forget that there was a time before RESTful microservices was the way to build web apps. And we are in a similar period in the data space. And as a software engineer, I find that really exciting, is that there's not just kind of off-the-shelf solutions you can go and take. And everybody's got a little bit of a different problem. And as somebody who likes to continue to learn and continue to develop personally, I find it sort of an interesting time. So like I said, some design principles around building data systems. So when I think about data science, and I particularly think about like what are the kind of key things about science that we can kind of bring to this space. And the two principles that stand out to me is that science should be reproducible and verifiable. So the idea of reproducibility is that if you have an experiment that you do in your lab, somebody can go and take and replicate your experiment in another lab. And they may get a same result or a different result, but that process can be reproduced and rerun. And also that the questions they're asked are verifiable, is that you can say, okay, we got this concentration of molecules out, like that there's a concrete answer, a measurable answer that kind of comes out of that. And so engineering is I think of sort of as the productization of science. And so, for example, if you are a drug researcher, maybe you spend some time in a lab and you invent some new molecule, and then a chemical engineer will figure out how to take that process and make it both more reliable so that you get more kind of consistent results and more scalable. So that, say, like where you might have a yield of 1% in your lab, you want to get that up to 10 or 20% in like a production quality drug pipeline. Similarly, you can think about engineering like reliability. Is just your bridge can't fall down. And so, like I said, I try to bring, like, throughout these talks, those would be the kind of 4 principles that I was going to inform the rest of kind of what we talk about, and kind of tools and recommendations that I'll make today. And so an observation to put with that is that, like, modern tools are infinitely scalable. So, like, modern data warehouses, tools like Spark for large distributed data processing are just, to me, as somebody who's been doing this for a long time, are just amazing. Is that they really, truly are, like, you give them enough computers and enough disk and memory and resources, and you can really throw just petabytes, as much data as you want. And the challenge is that humans aren't. Is that that you can't, you can throw a petabyte of data at Snowflake, but you can't throw 1,000 engineers on one project, right? Is that we need sort of, in addition to the technical scalability, we also need to think about tools and methodologies that let our teams and our development process scale as well. And the solution I take to this problem is, like, choosing appropriate tools and matching them to use cases, and then using those tools as directed. And so what I see in my consulting business a lot of times is that, and I say this not critically because I was this person else, is that an engineer will go read some blog posts and be like, oh, this tool is really shiny and exciting, I'm going to use that. And then they will go and then, might not be appropriate. So for a long time, I saw a lot of people using DynamoDB, which is, like, really expensive and great if you have a lot of high traffic volume, and people were using it for small stuff. And then the problem would be that then they like would get excited about it and then, like, not read the directions. And so, for example, if you try to treat a columnar data store like Snowflake, like MySQL, you're going to be in for a bad time. And so it's really kind of the combination of these two things, of sort of choosing appropriate tools at a technical level as well as your human level, and then, like, actually taking the time to read the documentation and understand how those work. Like I said, this is exciting times. Like we're at a point to sort of figure out just how do we do this. And as somebody, as like a hands-on practitioner, like, that's a lot of fun for me. I mean, I banged out Django sites for a long time, and it's fine, it's good, but, like, that's kind of a solved problem at this point. And so, yeah, like I said, working in data in 2022 presents both challenges and opportunities. All right, so, like, kind of let's get into it. So orchestration is what I think of as sort of like what makes your data platform go. And so this is just a mock diagram of a pretty simple data platform. It's actually fairly minimal. You can imagine, as you sort of graph these things out, that start having, like, dozens of data sources and, like, tens of processing jobs and kind of a bunch of different outputs, BI and CSV files or whatever. And so orchestration is the arrows. Like, orchestration is the arrows in your data platform. And so this doesn't have a label in this diagram, but you can see this is pretty central and really important to making things go. And so I like to think of orchestration as, like, the recipe for baking a data cake. So it's like, okay, go to the fridge and get out the eggs, and go to the pantry and get out the flour. Right? Maybe that's like ETL ingest. And it's like, okay, like, measure out the flour and mix everything up. Maybe that's your transform, stuff like that. And so it's basically all of the steps you need to do to execute your platform, and then, like, to execute, like, your data pipeline, and then actually does the actual running of it. And so the leading orchestration tool, these days is called Apache Airflow. It was developed by Airbnb and then open sourced, and there's really a thriving community of both users and companies supporting it. Their Slack group has 18 or 20,000 people on it. It's used by companies large and small, Google, Apple, Facebook. There's hosted solutions available. Amazon has a version called MWAA. I'm blanking on what GCP's is called. There's an excellent third-party hosted platform called Astronomer. And like everything else I'll be talking today is all of these tools are open source. I've been using open source my whole career, and I'm a really big fan of being able to look under the hood as well as not having vendor lock-in. And that said, hosted open source is great as an option, but just as long as, you know, like I'm always a little cautious around proprietary tools. And so Airflow, in my experience, is just vastly superior to using cron jobs or Lambdas for this purpose. And so when I run my classes, I'll take surveys about what people do, and a lot of times they say, "Oh, you know, we have a bunch of tasks, and you know, we just schedule them in sequence with cron." And so the challenge with that is like, okay, if your first data load job usually takes 8 minutes, and then you have a couple transform steps after that, say, okay, we're going to put our first one in, and then 10 minutes later, just give ourselves a little padding, we're going to run the next step. And so the risky thing about that is that, well, if for some reason your first step takes 12 minutes, you overshoot your window and your next job is running on stale data, and then everything breaks down. The converse is that if for some reason it only takes a minute, you're then sitting there idle for 9 minutes. And like debugging these things is not easy. You know, there's like no kind of really good centralized way to sort of look at everything that happened. Stuff like that. Lambdas have kind of similar problems. I'll show you an example a little bit later, but just where like without a central architecture to kind of glue everything together, it rapidly kind of devolves into a big messy spider web of stuff. And so things I like about Airflow, it's just Python. Is you just write a kind of DSL on top of Python. You can write pure Python code. The nice thing about that is, aside from being a language that we're mostly familiar with, is those pipelines become reusable. And so you can write a pipeline and reuse it like in the same way, a very similar way that you would do subclassing. And so like you can't really do that with a cron job. Like each one is a one-off, and you kind of wind up copying and pasting code, and it's painful. Airflow has some pretty amazing dashboards. I'll show you these in a second. It also ships with a whole bunch of providers. There's like 100 or 200 different providers, and these are like third-party shipped by Airflow, and also like third-party packages for doing all of the stuff you often want to do. So if you want to copy a file from S3 and load it somewhere else, there's an operator to do that. If you want to run data quality checks with a tool called Great Expectations, which we'll talk about, there's a tool to do that. If you want to kick off a Spark job, there's a tool to do that on your self-hosted Spark cluster, as well as Amazon's EMR. And so really just a lot of those, like in this Python philosophy of batteries included, like much of what you want to do in your data pipeline, like Airflow has these things, it's like 3 lines of code, whereas to hand code that up in cron is like, you know, maybe 30, like you got to write all this stuff yourself. The final thing that's cool is that Airflow is testable. And so there's a additional piece of software called Whirly, which like lets you spin up a local Airflow stack and like run your pipeline and write tests against it. You can say, hey, like if downloading the file from, you know, an API source failed, like go to this branch, you know, and send an error code, you know, and if it succeeds, go to this other thing. And so you can actually write unit tests for that the same way you would for the rest of your code. So this is just a quick little high-level overview of some of the Airflow dashboards. This is like the front page, and these shows you all of your different pipelines or DAGs and kind of their status of when they last ran and what their schedule is, and like the recent, like the individual tasks that are in there. And then you can kind of click through on those and get this nice graphical view of all the steps that can take. And so the neat thing about this is that Airflow, as treating the orchestration problem or the graph of tasks as like a first-class entity, is able to do things that you're not able to do with Lambdas or in cron by hand. And so in particular, it can figure out that the run me 0, 1, and 2 are independent of each other and can be run in parallel, right? But all of those have to run before this run after loop, for example. And so you can't do that, like you can't do that as easily by hand. And so this Airflow, you just get this for free. Like you just write your code, and Airflow figures out for you, hey, I can do all these things in parallel. Right. So everything's really faster. That's cool. It also has this kind of like history chart, so you can see the history of individual runs and like when each step ran, and we get like a nice little color-coded thing to say, oh, did it succeed or fail? And then, so you can also then like click through on each one of these things and get not only to the source code for that task, but the log files for that particular execution. And so as an operator of a data platform, this is just really superior to digging through CloudWatch logs on AWS, which if anybody's had to do, I have, and it's not fun. And so just this sort of higher level tool just kind of makes us as developers a lot more efficient. Other things I like about Airflow is that the execution is really excellent. And so you can get alerts by email or chat. So if a task fails, you can get a message to your Slack channel or your Microsoft Teams chat, like directly from Airflow, or it can send you an email. It has a built-in scheduler. So if you want to run things like on a cron-like schedule, you can do that like right in there and then, see it in those dashboards. It also has sensors. And so sensors are a way of, rather than driving things off of time, you can drive things off of events. So for example, if you wanted to do logic like a new file showed up on S3, run this whole pipeline to process it. That's like 2 lines of code in Airflow. And that's just, kind of a really powerful facility. And sort of then beyond that, the things that it adds over cron jobs or lambdas are like all of the like operational considerations. So retries. So sometimes, sometimes your task might fail and you just want to retry it. Like, hey, API endpoint wasn't reachable. Like, just wait a minute and try again. Like hand coding this repeatedly gets tiresome. You also get the reporting on it. You get metrics, so you can wire Airflow to talk to CloudWatch or Prometheus or Datadog, and have like historical statistical reports as well as alerting on like how long did particular tasks take to run. And so this is a way of sort of monitoring, like, oh, okay, maybe this ETL task, that used to take 5 minutes is now like, well, last week it's, when we wrote it 6 months ago, it took 5 minutes, and then last month it's taken 15, and now it's taken 30. It's like, okay, maybe somebody needs to go look at that. And so by putting that into a dashboard, much the way you would, your web traffic, like you kind of alluded. And then the final thing that's really cool is resource limits. And so because it has a global view of your entire data platform, you're able to say things like, only allow a maximum of 3 connections across all of my pipelines to our production database. You can't do that. You cannot do that with cron jobs. You cannot do that with lambdas. It requires something that has this sort of centralized view. And so, like I said, this is a really great tool, and kind of can be adopted. Can transition to it on the side. So, all right, we're just gonna keep flying on here. So data quality, correctness in data platforms is hard. Correctness is like really hard. And the biggest challenge, I think, is that there's no right answers. And so if you have a bunch of SQL statements or a Jupyter notebook with some pandas code, and it runs an analysis and the answer you get out is 42. Is that right? I don't know. You probably don't know. And unless you're going to go do a separate implementation of it in Excel, or like re-implement some other thing to say, okay, do we do this correctly? Like, there's not really a way to know. And so this makes testing really difficult. It's not like there's a well-defined behavior like there is in a web app, where you click a button and a row is written to a database and the email gets sent. Like this is technically, there's no oracles. Like, there's no way it says like, yes, that's correct. The other challenge is that data may change over time. And so maybe the answer today is, for your sales figures for New York State is 42,000. And next month it's, negative 9,063. Is that right? Is that reasonable? I don't, who knows? Who knows? And so, needing to put some sort of guardrails on the real world data as it comes in is also important. And the reason this matters so much is that bad data is like radioactive. So once it gets into your system, it's like toxic waste, and it just kind of gets everywhere. And it's very hard to clean up, and it can be very hard to detect. And that has like real world consequences. And so like in a web app, if 1 in 10,000 or 1 in 1,000 users like their shopping cart disappears. Like, okay, well, that's too bad. But it's not, in the grand scheme of things, not terrible. Whereas just the size and the consequence of the decisions being made on top of data stacks is really important. And so, for example, like with that New York sales thing, like you get some bad data in there, and then like somebody goes and like makes a decision on like, oh, okay, well, sales are down in New York. We need to spend more money on marketing in that state. And then you come back like 6 months later and be like, well, actually they weren't, and our data was just bad. And it's like, well, somebody went and spent maybe like hundreds of tens of thousands of dollars based on that bad data. And so the impact of any one particular bit of data being wrong is kind of more significant. The final point that makes all this hard is that the stacks are really complicated. As we like looking back at that previous diagram, there's like a lot of moving pieces, and it's sort of hard to write tests for this. A really helpful tool in this space is called Great Expectations. And so Great Expectations implements like runtime quality checks. And there's like a couple hundred of these things. I'll show an example in a minute. And so this is on your live data. This isn't unit tests, but sort of much like you would do with model monitoring for model drift. And so this works with CSV files, it works with Spark, and it works with any SQL, like any SQL database. You also get these cool free reports I'll show you in a second. And so what does this actually do? And so it lets you write basically like heuristic-based guidelines around your data set. So you can say every row in one table with a foreign key those foreign keys should have a corresponding primary key in another table. You can do things like if we'll have an ETL job to load some data, if 5% of the values in a particular column are null, that's a warning. If 10% are more null, that's an error and fail the whole pipeline. And so, like I said, this ships with like, I don't know, maybe about 100 or 200 of these different kind of things. There's also more sophisticated statistical checks you can do, where you can say, if the value of this column is outside, 2 standard deviations from where it was in the previous month, like throw an error. And so like I said, it just sort of lets you put some like sanity checks on your data process. You also get these cool free reports that make debugging really helpful. So each time you run it, each of those checks spits out like what the test was, as well as like basic statistical properties. And so these are like static HTML files for each execution. You can save these, and you can kind of use those to go look back and say, oh wait, something went wrong. Where you said, okay, the median or the 95th percentile of this field was 5 this month, and like 3 months ago it was 2. Like, okay, that gives you some sort of something to start looking at. How do you use this thing? And so basically what you want to do is you want to define those metrics. Like you want to figure out like what are those heuristic checks that you're concerned about. And that's going to be specific to your problem. And then you set alert and fail levels. Like I said, it could be 5% nulls is an alert, 10% is an error. And then this methodology is based on what Airbnb does. Is they do what they call stage check exchange. And so you want to load your data into whatever platform, could be your CSV files, could be your warehouse, check it for correctness, and then exchange it into your production tables. Because you have like concurrent active BI users or active like reporting tools on it. And so before you like promote that data to being production worthy, you need to actually verify that it's correct. And so like you kind of load it in a temp table, run your checks, and then swap it out. The other thing is that you want to run a check after every step. Like every step of your data pipeline should have a corresponding check. And so in that diagram we showed earlier, with the Airflow DAGs, like each loading job, like you load the data, you check it, then you do the transform step, you check it. You do another transform step, you check it. And so the idea is you want to catch problems as early as possible, both because it makes your code a little more modular, it makes it easier to debug, and like I said, like you want to just sort of detect these things before it heads downstream and becomes really problematic. Okay, some other tools in this space. DQ does this for Spark. Evidently is a tool for ML modeling, model monitoring. So for example, like if you train a machine learning model in, 2015 on news articles, it's going to be really confused by 2017 when Donald Trump is president. And so your model may be correct, your statistics are correct, but the underlying world has changed. And so this is the kind of thing we're trying to catch with quality checks. TFDV does a similar thing to Evidently for TensorFlow, and assert R is kind of a similar package for the R language. Okay, we're going to keep flying along here. Reusable SQL. So I've been writing SQL since 1998, and this cool thing we'll show here real quick called DBT is the first time I have been able to reuse SQL the same way you reuse code. And so it is based on Jinja. Jinja is the native template language in Flask, and it lets you reuse SQL the way you can, same way like Python subclasses. And so it's an absolute game changer. And so to the point where I will recommend to my clients the choice of a data warehouse by whether or not it has DBT support. And so the cool thing is that the way it works is everything is a select statement. You don't write inserts, you don't write updates, you don't write create table things. DBT just does it all for you. All you write is select statements, and then it figures, and then in this config file, you can say, hey, implement that as a materialized table or implement that as a view, and it just does it for you. It also deals with all the dependencies of say oh, we have to have this table built before this next one. It just figures this all out for you. Here's a quick example of what this looks like. And so this is a model to sum up the payments by type on an order. So let's say you could pay by bank transfer or credit card or gift card, and you can have multiple payments. And you want to just on each order say what are the different methods? And so basically, we have this variable that has a list of payment methods, and then we're going to loop over it and generate SQL based on each of those. And so if you were just doing this in raw SQL by hand, you would have to spell out this some case each time for you'd have a bank transfer amount, a credit card amount. And so that gets if you then add another payment method, you have to copy paste in yet another line. And then, for example, let's say, okay, we don't want the sum of payments, but we want the count of each type. Well, now you've got to change it in 3 or 4 places. Where instead, this is lets you kind of reuse your SQL. There's also macro support, so you could write a little snippet that does this kind of loop, and then apply it to not only your orders model, but maybe your refunds model, stuff like that. And so, like I said, this thing really, really amazing, and I cannot recommend it highly enough. So why use DBT? So the main thing is that it enables self-serve. And so data engineers are a cost. We provide the infrastructure that lets people do the actual work that provides business value. And so DBT is simple enough that you can take somebody who is a data analyst and teach them a little bit of SQL. It's not too hard. And they become analytics engineers, that they're able to write and deploy new models themselves, whereas 5 years ago, you used to have to go back to your IT department or your software development department and be like, hey, write me a new Spark job, right? You can just have somebody just write this, once it's all set up. And so that lets data engineers focus on platform and technical problems instead of the business logic, and you can deliver more business value with fewer data engineers. So I introduced this to one of my clients 4 or 5 years ago, and they had been planning to hire 5 data engineers and 2 analysts. And because we were using DBT, they were able to flip that around. And so they hired instead 2 data engineers and 5 analysts. That's a huge win. That's a huge win. It's because it's the analysts who provide the business value. And so this really just lets those people operate more independently and kind of get more stuff done. All right, so other kind of good stuff. So I know this is largely a data science conference. Everybody loves their notebooks. I like them too. The challenge has been how do you take a notebook that somebody developed on their laptop and turn that into a productionable service that runs automatically, stuff like that. A really good tool for this is called Papermill, and it lets you run Jupyter notebooks like a Python command line script. And so this is sort of deceptively simple. And so what you do is you tag one of your cells called parameters. You see this up at the top. And the variables defined in that cell become accessible as command line arguments through Papermill. So here we have one called ratio, and we'll run this under Papermill, and then it will execute your whole notebook. Instead of using 0.1, it will use 0.3 because that's what you passed on the command line. And then the output of that, aside from whatever side effects it has, is a new notebook. And the cool thing about this is that it's like this superpower interactive log, is that you can then go and look at what actually happened. And so instead of just log files, maybe you generate some histograms as an aside. And so you can see for each execution what that actually was. And so this is how Netflix runs all of their data science and data engineering jobs. All of them are done with Papermill. There's also Airflow support. So you can take a Jupyter notebook and do this, and then run it directly in Airflow with no other code modification. And so again, this just sort of minimizes the amount of work your data engineering team needs to do to kind of get things into production. Some other cool tools in the notebook space. nbdev is a nice suite of tools for notebook integration. So this complements Papermill really well. It lets you run your notebooks as unit tests. So you can put a bunch of assert statements in there and tag your cells as those are testable. And then it will run it the same way you would use a PyTest test. You can also export print-ready documents and articles, which makes data scientists really happy. Is that from your same notebook that you would run in production, you can generate HTML documents for other users to use, as well as print-ready PDFs. On the engineering side, you can also take your Jupyter notebook, and again, you label which cells, and it will export and build a PyPI or a conda package for you, including the setup.py. And so rather than having to do the work, and so then that's then a library that you can then use in another application that, without having to run a notebook. And so rather than having to do the work by hand of okay, well, I wrote this whole notebook and now I need to extract the functions and the libraries within it, it says you can just use these tooling, and that reduces the manual work, and then you update it, things don't get out of sync, you just run it again. Other fun tools in this space, nbdev stands for Notebook Diff and Merge. And so it's basically git diff and merge for notebooks. And so if anybody's ever looked at a git diff of a notebook or compared branches of notebooks on GitHub, it's totally useless because it's nothing. So nbdev is specifically a notebook aware diff tool. So it makes those kind of code reviews easier. NBQA adds linting and quality checks, source code formatting on top of notebooks, black, things like that. Like I said, just being able to meet people where they're at as an engineer. It's my job as a data engineer is to facilitate other people's work. And so if people want to use notebooks, great, let's use this stuff and figure out how to get more stuff done. Okay, a little bit on the ops, DevOps and developing front. So like I said, one of the goals here is reproducibility. And so that looks like reproducible builds, so that your software should always be the same, that this process should be fully automated, and that your tests should be similarly reproducible. And so the number one thing you can do to guarantee reproducibility in your software is dependency pinning. So requirements.txt is your file list of all your Python dependencies. And so what I see a lot of people do is they just say install TensorFlow or install pandas. And really what you want to be doing and saying is install a specific version of TensorFlow, or specifically pandas 17. And the reasons for this are twofold. One, so that all of your developers have a consistent software stack. And also two, is so that in CI/CD, you want to make sure that you deploy the same code that you test. And so what can happen with the thing on the left is maybe you install pandas 17 and run your tests and they pass. And then before you get to deploy your code, pandas 18 is released. And maybe there's an incompatibility. And so it breaks. And so you want to make sure everything is exactly specified. Whereas the thing on the left just says, oh, hey, go get the latest version. And so like I said, this is kind of the most basic principle of reproducibility in software I can kind of come up with. On CI/CD is so everything has to be automated. And so that means no building models on your laptop. And so, I'm sure we'll have the experience of oh, where does the recommendation model, how does that get built? Oh, well, Joe builds it. What happened to Joe? He quit 2 years ago. well, okay, that's not good. Like, how do we update the model? Or like maybe Joe drops his laptop in the bath. Or even if none of those things go wrong, like having this be a manual process is error prone. And so like you might even have a well written out of steps, but like do you actually execute them correctly? And so you want to have everything in your build process, like of your software, of your models, be automated. Similarly, like you want to test what you deploy and deploy what you tested. So if you're going to build the Docker image, you run the test in the Docker image, and it's those particular bytes of that Docker image are what you actually push to production. And so, right, like you're deploying the exact artifact that you tested. And so this can be a bunch of work to set up. But the nice thing is that like once you have it in CI/CD, it makes setting up a local development environment almost trivial. And so I'm sure we've all had the experience of starting up with a new job or a new client, and it takes like a week to get a working development environment set up. And then once you've got it set up, like you're never going to touch it again. And so your thing is like totally different than everyone else's. And so automating both your CI/CD and your local development environment, like just makes this process more reliable, much faster, much smoother. Like when we say, hey, we're going to upgrade our dependencies, like everybody can just push that out and like get all those changes at the same time. And so like less spurious errors, stuff like that. On the subject of testing, tests really need to be comprehensive. So you want to cover like as many cases as you want. And so you should never use live data for testing. That's not a test, right? Like to test, you want to basically say, I have this known input and I like have the same output. And if your underlying data is changing, you can't really do that. And so a lot of see people, sometimes they just say, oh, like we ran this script and like there's, we just checked that the right column showed up. That's not really a test. Like maybe you have the right column, but they're all zero. Like what have you tested there? And so the solution to do this, like I said, like it's not like there's necessarily a right answer, but I think the best thing you can do is consistency. And so say, hey, with this input set, we got this output. So we like took this CSV and the output was 42. And the reason you want to be able to do that is so that if you then go back and optimize your SQL statements, you optimize your pandas script, to be more efficient, or maybe you found an error, you want to be able to say like, hey, the business logic shouldn't change. With the same input, do we get the same answer on the output, despite the fact we changed the code? And I think that's the best you can do in the data space. The way to do that is what are called fixtures. And so this is like pre-baked sample data for using for inputs. So like rather than live data, you have like, input test.csv, and you will always run your tests against that. A helpful tool in writing tests is this thing called coverage. And so coverage shows you what you're testing, and it like lets you improve your test via gamification. And so I, like everyone else, like I don't really like writing tests. It's boring. The nice thing is once you have them is then you can just rip on your development process. So like, hey, I have that test, answer's 42. I optimized it, test passes, I'm done. Like I can just make those changes with confidence, and the test pass, and deploy them, and we're just going to keep going on to the next thing. But the work of getting those initial tests in place can be kind of dull. And so what coverage does is it like instruments your Python code and is able to detect specifically what your tests are exercising. And then it will give you this report and show you what percentage of your source code file actually got run. And so this is a way of like making this process like a little bit more like a game. So I can come in and be like, okay, the makefiles.py only has 19% when I started at 9 a.m. And at the end of the day, I was like, okay, well, my goal today is just get that number up. And so I go home at 5 p.m. and I'm like, all right, it's up to 90%. And I feel like I accomplished something. The corresponding thing is that it will also give you an annotated version of your source code. And so it's able to tell specifically which lines of your source were exercised by your test. And so this is helpful for two reasons. One, in that gamification process, it lets you know what you still need to target. But it also lets you verify that your tests are actually doing what you thought they were. So here's an example. This is for some XML parsing, and the test doesn't cover some of these error cases. And so maybe you wrote a test that you thought did, but you wrote your test wrong. And so coverage lets you say like, oh, actually, like, does my test code actually cover like what does it actually do? I think it's probably about the last thing I had to talk here. And so last thing I kind of is like, I'm still a little surprised about this is version control. So again, with the principle of reproducibility, like you should never have to ask what's running in production. Like you should just know. You'd be like, it's this version of the code, and this is how we built it, and that's how it got there. And so in the data space, this is challenging because, like, particularly in model building, the line between code and data is like not as clear as it is in other spaces, right? Like, so your output artifact is a scikit-learn model that depends not just, the inputs is not just the source code used to produce it, but also like the training data. And so DVC is like Git for data plus code. And so it runs next to your regular, very similar commands to your Git stuff, the Git commands you're used to. It's got notebook support, but it's also able to deal with like external data sets. So if your source data, like, 'cause you don't want to put huge files in Git, it's not so great. But if you got like some really big Parquet files on S3 that you're going to use to train a model, DVC can be aware of that and version control those like next to your source code, so that each commit on your Git code also has a corresponding commit like of the data. And so this lets you achieve like reproducibility for your machine learning models. Like it has a runner that you can use in production, as well as also like let you do experiment tracking. So you can be like, okay, well, I did this stuff, and it's like, well, the results last week were better. It's like, okay, how did you make them? Like, what was the source data? And so DVC, like in the same way that Git gives you a time travel for your code, DVC kind of lets you do like right next to it for your data. And so just to kind of wrap up here, like I said, so data science in production should be like reproducible and verifiable, as well as scalable and reliable. And so I've hopefully given you some kind of tools and techniques for how to do that today. These are the specific tools we talked about. So Airflow for orchestration, Great Expectations for quality checks, DBT for reusable SQL, Papermill and nbdev for running notebooks in production, coverage for testing, and DVC for data version control. And so some of the techniques you're going to use along with that are like full automation and this dependency pinning, as well as kind of text fixtures. And so like I said, like this is a little teaser of a 3-hour class. That 3-hour class is the short version of what will eventually be a 300 or 400-page book. Each topic of that short class is also then it's like another 3-hour class. And so I'll be teaching a longer version of this that kind of goes into more depth about these topics and a whole bunch more with Geekle next Wednesday, December 1st. Maybe it's Thursday. 11 to 3 p.m. Eastern. I would love to see you there. We'll have a little more time for kind of more interactive stuff. I also teach it again online on the O'Reilly platform on February 15th. And you can find more of my classes on my website. Thank you so much. I hope this was useful. And yeah, if there's any questions, I'm looking forward to taking them in the Q&A.